Hello and welcome to another video in the series on partial fraction decomposition. In this video, we are going to do a couple demonstrations that involve non-monic denominator polynomials. These are polynomials that do not have 1 as their leading coefficient. So our objectives are to demonstrate the techniques of partial fractions with denominators that have a leading coefficient other than 1. We're going to do a couple examples of that. And we're going to compare different decompositions when the leading coefficient in the denominator is not 1. But we'll see that all of these decompositions are equivalent and the uniqueness of partial fractions is maintained. So materials for review include factoring polynomials, the quadratic formula, because we'll use that, the complete factorization theorem, and algebra with fractions, because we're going to need that in order to recombine our templates. So using the complete factorization theorem, okay, consider the rational function -3 over 2x squared minus 3x plus 1. We check the degrees of the numerator and the denominator first to make sure it's a proper rational function. In this case it is. The degree of the numerator is 0, the degree of the denominator is 2, so we may proceed. We're going to go ahead and factor the denominator, but we'll go ahead and use the quadratic formula to get the roots, and we'll have x equal 1 and x equal 1/2 as the roots. So the complete factorization theorem says that we can factor 2x squared minus 3x plus 1 as 2 times the quantity x minus 1/2 times the quantity x minus 1. And the details here demonstrate that we do get back to our original denominator polynomial. So we may rewrite our rational function as -3 divided by 2x squared minus 3x plus 1 as 1/2 times the quantity a divided by x minus 1/2 plus b divided by x minus 1. Remember, we're going to try to find out what a and b are. Now that we have our decomposition started, we can proceed with our substitution method. If we focus our attention on the two fractions inside the parentheses, we have a times quantity x minus 1 plus b times quantity x minus 1/2. All of that divided by x minus 1/2 times x minus 1. And a little bit of simplifying here gives us a result. And the result that we're looking for here is that when we use the substitution technique with x equal 1 first, we eliminate the a variable and we end up with 1/2 b equal to -3. And that means that b is going to be -6. If we use the substitution technique with x equal 1/2, this eliminates the b constant, and we have 6 is equal to a when we go through the details of the arithmetic. So our decomposition can be rewritten as follows. The rational function -3 divided by 2x squared minus 3x plus 1 can be rewritten as 1/2 times the quantity of 6 divided by x minus 1/2 plus -6 times x minus 1. Now, if we simplify things down by distributing the 1/2 on each of these fractions, we end up with 3 divided by x minus 1/2 plus -3 divided by x minus 1. So when we do not use the complete factorization theorem, remember the complete factorization theorem factors out the leading coefficient and just has x minus the roots as our factors. But if we don't use the complete factorization theorem, we may factor 2x squared minus 3x plus 1 as the quantity 2x minus 1 times x minus 1. And when we do this as our template for our decomposition, we end up with a times the quantity x minus 1 plus b times the quantity 2x minus 1, all of that divided by the product of the factors 2x minus 1 times x minus 1. In this case, we're going to set up a system of equations and we're going to match up the coefficients. Here we have -3 is equal to -a minus b. That's the constants. When we match up the constants, this is the equation that we get. The x coefficients gives us that 0 is equal to a plus 2b. That's the equation that matches up with the x coefficients. So solving by eliminating a is going to yield that b is negative 3. And substituting this value of b into the equations gives me that a equals 6. So the decomposition of negative 3 divided by 2x squared minus 3x plus 1 is 6 divided by 2x minus 1 plus negative 3 divided by x minus 1. Now we're going to compare these two examples. Examples 1 and 2 are the same rational function. So when we did it by the complete factorization theorem, we ended up with 1/2 times the quantity 6 divided by x minus 1/2 plus negative 6 divided by x minus 1. When we didn't use the complete factorization theorem, we ended up with a decomposition that was 6 divided by 2x minus 1 plus negative 3 over x minus 1. And the question is, are these identical? Because if they're not, then we have violated the uniqueness property of partial fractions. But in this case, they are. If you distribute the 1/2, you'll get 3 over x minus 1/2 plus negative 3 over x minus 1. Rewriting that x minus 1/2 denominator with combining fractions is going to give me 2x minus 1. But all of that's going to be divided by 2. And we know that by the flip multiply rule, we'll have 3 times 2, which is 6. So both of these decompositions do, in fact, give the same result for this rational function. So uniqueness is not violated. Even though the values of a and b are different, the overall decompositions are identical, different ways of writing it. But this is something that we want to be careful of, because in many cases, dropping the 1/2 factor in front by using the complete factorization theorem can lead to errors. In this example, we're going to compare the placement of the leading coefficient. So we're going to consider the rational function x squared divided by 4x cubed minus 8x squared minus 4x plus 8. The degree of the numerator is 2. The degree of the denominator is 3. It is a proper rational function. And if we factor the denominator, we have 4 times the quantity x minus 1 times the quantity x plus 1, and that's also times the quantity x minus 2. So our decomposition may appear as any of the following forms that you see on the slide. We could have a divided by 4 times the factor x minus 1, plus b divided by the factor x plus 1, plus c divided by the factor x minus 2. But we could also have a decomposition template that looks like a divided by x minus 1, plus b divided by 4 times the factor x plus 1, plus c divided by the factor x minus 2. We could also have a divided by the factor x minus 1, plus b divided by the factor x plus 1, plus c divided by 4 times the factor x minus 2. Each one of these are still equivalent. And of course, our final one could have the 1/4 factored out from the denominator entirely and have 1/4 times the quantity, a divided by x minus 1, plus b divided by x plus 1, plus c divided by x minus 2. So each one of these templates for the decompositions are valid algebraically. So the question is, how does this affect the values of these coefficients, a, b, and c? And that's what we're going to discover. So we're going to choose which decomposition we're going to use, and this matters, of course, because the placement of the 4 is going to have an influence on the values of the coefficients. But by the uniqueness property of partial fractions, they will all be identical through algebraic manipulations. So the next slides are going to demonstrate all 4 decompositions using the substitution method, sometimes referred to as the Heaviside cover-up method. When we start with using x equal 1 in our decompositions, we're going to go ahead and find a. Now on the left side of this, we have 4 in the denominator of the a fraction, where on the right, we have 4 in the denominator of the b fraction. And when we do this substitution method by using x equal 1, we end up with negative 1/2 equal to a when 4 is the denominator under a. But when it's not, we get negative 1/8 for the value of a. So this is the difference that it makes. But because 1/4 of negative 1/2 is negative 1/8, the decompositions, or at least the that part of the decompositions, are still equivalent. Okay. When we use x equal -1, okay, in our decomposition, we can find out what the value of b is. Now, again, on the left, we have 4 as part of the denominator for the a value. And when we do the details of this substitution, we get 1/24 for b. On the right, we have 4 already in the denominator under the b value itself. So we get b to be 1/6 when we do this substitution method. And again, because we already have the value of 4 in the denominator under b, 1/6 times 1/4 is 1/24. So the values again are the same. Okay, in the overall viewpoint of the decomposition. But this is how the placement of the leading coefficient has an effect. When you use x equal 2 in our decompositions, we can find out the value of c. And again, when we put 2 into our value for x for substitution, in this case, we get c to be 1/3 for both of these because neither one of these templates involve 4 in the denominator of c. So they're identical. So our decompositions for these guys could be written as -1/2 divided by 4 times the factor x minus 1 plus 1/24 over x plus 1 plus 1/3 over x minus 2. That's if you put the 4 underneath that a value that we tried to find. When you put the 4 under the b value that we tried to find, we ended up with -1/8 x minus 1, or divided by x minus 1, plus 1/6 divided by 4 times x plus 1. So here you can see how the values of the coefficients are different, okay, based on the placement of the leading coefficient. And then plus 1/3 over x minus 2 again, because we didn't have a division by 4 in these examples here. The placement of 4 does not change the decomposition. It merely changes the value of the coefficient where that denominator has been altered if I choose to incorporate that leading coefficient as one of these denominators. Now we're going to see what happens when I compare putting the placement of 4 under the c as opposed to not having 4 involved in any of these fractions, leaving it out as a separate factor to be handled later. When I put x equal 1 for the substitution method, I get -1/8 is equal to a. When I have the 4 underneath the c value, I get -1/2 is equal to a when I leave 1/4 as a separate factor for this decomposition. Okay, now you may look at this and say, well, these values are different, but remember, the values on the right are all going to be divided by 4 or multiplied by 1/4, and so they will still match up. When we use x equal -1, the same kind of behavior occurs. We have 1/24 for the value of b when the value of 4 is under the c fraction. When it's factored out of the complete template, it's 1/4 times the sum of the fractions, we get 1/6. And again, 1/4 of 1/6 is 1/24, so the values in the decomposition are the same, even though the specific values of finding a, b, and c are different because of that placement of the leading coefficient. When we use x equal 2 in our decomposition, we have the value of c being 4/3 for both of these, because technically speaking, the factor of 4 is in fact in the denominator of both of these fractions that contain that c value that we're trying to find. So when we compare these two decompositions, we could have -1/8 divided by x minus 1, plus 1/24 divided by x plus 1, plus 4/3 divided by 4 times the quantity x minus 2. Notice that those 4s will cancel and give you that c value of 1/3 that we saw before when I was doing the substitution methods when 4 was under the denominators for a and for b. If I leave the factor of 1/4 out completely from the fractional parts, just leave it as a separate factor, I end up with -1/2 divided by x minus 1, plus 1/6 divided by x plus 1, plus 4/3 divided by x minus 2. And this is what happens to the values of a, b, and c when the leading coefficient has been completely factored out and will be addressed later in the decomposition. So this example demonstrates the importance of handling leading coefficients correctly. The placement of the leading coefficient influences the values of these coefficients A, B, and C in the decomposition. It also demonstrates that once it's factored, it doesn't matter which factor receives the leading coefficient or if any of them receive it. You could leave it completely out of the summations of those individual fractions. But the important thing is the leading coefficient is not dropped or forgotten while performing the decomposition. Because in the end, the decompositions are identical by the uniqueness property of the partial fractions. So you can move the 4 into one of those fractions, referencing our example 3. You can move the 4 inside one of those fractions, or you can leave it completely out. The coefficients that result from trying to determine the partial fractions are influenced by this, but collectively, they will still be the same decomposition. Thank you for your time and attention.